rod. So you have a rod of length L and mass M. Okay, the center of mass would naturally be in the center of this object because we're assuming the mass is evenly distributed. If we were to carve out a little section there, we see that in red, it would be a fraction of the mass as well as a fraction of the radius of the whole object. So that little strip there represents dm, some really, really infinitesimally small mass and some really, really small radius. So we know that I, the moment of inertia, for any object is equal to the root integral of r squared dm. We need dm in terms of dr, okay, so we can take that integral. So let's make up a proportion here. So m, the mass of the rod, is to L, the length of the rod. Let me keep that cursive, keep it consistent. As dm, that tiny, really, really small mass there, is to dr. Okay, so we want dm by itself, so we're going to cross multiply and then divide both sides by L. So be left with dm is equal to big M times dr divided by L. So, okay, so what we want to do here is substitute in dm into our integral and simplify a bit. So we're going to get the moment of inertia is equal to the integral of r squared times big M dr over L. We see that M and L, the mass of the rod and length of the rod, will not change. Those are constants. So we can bring those in front of the integral. We're going to have M over L times the integral of r squared dr. Okay, so let's think about bounds of integration here. So this rotational inertia, which we assume to be at the center of the mass of the object, from the end of rotation could at maximum be from 0 to L over 2. Okay? But there are two sides of this rod here. So we have from 0 to L over 2 and then from 0 to negative L over 2. So we do want our bounds of integration to be from 0 to L over 2, but to account for that symmetry, we need to multiply the whole integral by 2. So we simplify that, okay? We're going to plug in 0 for r and L over 2 for r once you take the integral. So let's write that out here. So we'll have 2m over L times 1/3 r cubed from 0 to L over 2. We plug in 0 for r, the whole quantity will simplify to 0. So what we're going to be left with here is 2m over L, technically 3L, times L over 2 cubed. Alright, so we need a little bit more room. Let's go to the next page. So we're going to have 2m over 3L times L cubed over 2 cubed. 2 cubed, we're going to get 8. So what's going to happen here is this L and the denominator is going to cancel out. In the numerator, it will simplify to L squared. This 2 in the numerator will cancel out, and this denominator will simplify to 4. 3 times 4 is 12, so we're going to get 1/12 m times L squared. So this is the moment of inertia about the center of mass for a rod. 1/12 ml squared. Okay. So zoom out for a second, take a look. Let's move on to the second most popular example in the AP exam, which is our disk here. So we have a disk of mass m, radius r. Okay, we see here that we're going to cut out a really thin shell. I know it doesn't look that thin on our diagram here. It's a little hard to draw with this software, but imagine a really, really thin shell, okay? Those shells are a fraction of the total mass and total radius of our whole disk. So a little bit different than our rod here is that we need to relate m and dm to the area of our disk and our really thin shell. So that relationship here, we're going to have big M is to pi r squared, big R, the radius of our disk, as dm, a really small strip of mass, is to 2 pi r dr. Okay, so again, we want to solve for dm. So we're going to cross multiply, divide both sides by pi r squared. We'll get dm is equal to big M times 2 pi r dr divided by pi r squared. Okay, so we know that the moment of inertia is equal to the integral of r squared dr, dm. We want to plug in for dm. We see, let's simplify a bit, that these pi's will cancel out. We know that m and r squared and this 2 are all technically constant, so we can bring them out in front of the integral sign. So simplify, we'll get 2m over r squared times the integral of r squared times r, which is really r cubed, gr, from 0 to big R. So 0, our center of our circle, all the way to the maximum radius of our whole disk. So those will be our bounds of integration. So simplify again, we'll have 2m over r squared times 1/4 r to the 4th from 0 to big R. So again, we plug in that 0, that whole quantity will simplify to 0. So we'll have 2m over r squared times 1/4. So we'll have that 4 here. R to the 4th. Okay, so we're going to see that r squared will cancel out of our denominator. In our numerator, this will simplify to r squared. And then 2 divided by 4 is a half. So we're going to get 1/2 m r squared, which is I, the center of mass, for a disk or a hollow cylinder.